that's why we do ATAM. So, ATAM. So this was proposed by Casman, and again, the reason he proposed this method is to analyze the consequences of your architectural decision and their alternatives in the light of QA requirements. Right? So this is to evaluate the fitness of the architecture, and we look at multiple competing quality attributes. So we're going to look at trade-offs, we're going to analyze the system as a whole, and the interactions. This is a spiral model of design. Okay, so this is risk identification, and then we're going to refine the system. So we're going to mitigate the risks, and the concept is going to lead to refine architecture. That's our main goal. Okay. So we want to find trends, we want to discover risks, and then we invest further time in mitigating these risks. This slide shows you the benefits of ATAM. So the question comes like this, you should know. Your quality attribute requirements, you're clarifying it in this process. Any kind of architecture documentation, if it's lacking, you'll improve it. You have some kind of documentation and the artifacts for architectural decisions, which is what you're going to share. You're going to identify risks, you will identify non-risks. Again, you will increase communication among stakeholders as well as project customer, so that everybody is on the same page. And the most improved benefit is improved architectures. ATAM vocabulary, again, when we talk about scenario, hope we all know, we have looked at it at the utility tree, you know who the stakeholder is, you know what a view is, you know what a FR is, NFR. When we talk about non-risks, these are good decisions. So if you're using object-oriented system or architecture, that's a non-risk. Risk is architectural decision in the light of QAs that are potentially problematic. Okay, that means if it is going to reduce, for instance, the performance of the system, that is called a risk to the system. Sensitivity points, again, we are probing through the architecture decisions, any kind of parameters in your architectural decisions where you can correlate that parameter to a quality attribute which is measurable. Okay, so for example, a sensitivity point where you are increasing the encryption level of your system highly correlates that particular decision to security increase. Okay, so that is called a sensitivity point. Trade-off: if you increase the encryption level of your system from 126-bit to say 256-bit, you have increased the security of the system, but a trade-off would be that cost is increased. Okay, so more expensive. So you increase security at the expense of increasing cost. You are increasing security, maybe the performance of the system decreased. Okay, that is called a trade-off. So risk, non-risk, sensitivity points and trade-offs are part of ATAM. In participants in ATAM, we have an external evaluation team, typically 3 to 5 people who are domain specialists. They should know the architectures. Project decision makers, they are part of this process, so we need to include the project manager, and obviously the architect is part of project decision maker because they are key to this whole process. Architecture stakeholders, they are roughly 12 to 15, and we need to include all the stakeholders, roughly all the stakeholders as part of this process. And you can see in this, what it tells you is the evaluation team itself, they set them up into different roles. And in some cases, the same person may take on multiple roles. For instance, one key person could be doing the scribe role and be the team leader. Okay, if you have less people, you can take on multiple roles. So outputs of the ATAM, the architecture is represented well. All the business goals are captured. The QA requirements are prioritized, again in the light of QA scenarios. And these quality attributes take the form described in chapter 4, and this is more like using a utility tree. A set of risks, non-risks, we're looking at risk themes in this process. The risk themes, We've already looked at this. We've looked at sensitivity points, trade-off points. Intangible outputs, so this is something you cannot touch. Obviously, there's a sense of community, everyone's on the same page. There is communication that has opened up, so everyone has a better understanding. And any kind of conflicts are negotiated and taken care of during this process. You can see phases of the ATAM. 0 is set up. 1 is steps 1 through 6, and this is when you have evaluation team, project decision makers. Steps 7 through 9 is when you bring in the stakeholders. And this is the follow-up, is when the evaluation team and the client meet. And you can see this is a lengthy process, it's a time-intensive process. The first is present the ATAM. You can see the different steps. So the evaluation leader will present the ATAM process, make sure everyone is on the same page. Step 2, business drivers, typically project decision maker, ideally the project customer, will show all what is relevant in terms of the business drivers, business context, the business goals, share who the stakeholders are, the drivers, and so on. Step 3 is presentation of the architecture. So the lead architect or the architecture team, they will show their thought process. They will show the architecture decisions, the architectural approaches, patterns, tactics, and so on. And this is what is presented during the system and during this step, and convey the architecture and talk about it. So this is someone who knows the architecture well. Step 4, identify architectural approaches. So in this, the evaluation team again has a good knowledge of the patterns, tactics that the architect has used. So they will catalog, means they will document patterns and tactics, and they will document it so that this is served in the next few steps for analysis. Step 5, the architect will generate a utility tree after consultation with the evaluation team, and you already know what this is. So the scenarios are ranked. We will prioritize the scenarios, and this utility tree will have all the scenarios in terms of importance and weightings. You all know what a utility tree is. Again, it shows the business value, architectural impact in terms of the weightings. And then you have different kinds of scenarios, like for instance, exploratory scenarios, growth scenarios, use case scenarios. You can split all that. Make sure that these scenarios shows what is significant and what we are interested in. What is the cause, what is the response? All that needs to be documented. And the most important thing is all these scenarios are specific. That means they should have some kind of statistics so that we can measure them as we go along. So step 6 is when analysis happens for all the approaches that are already presented. And the architect has led this approach. So evaluation team now goes through, and this is when they're going to identify risks, sensitivity points, trade-offs, and document them. They catalog it, right? And this is when they will turn to for deep analysis. Steps 7 to 9, you bring the stakeholders, show them the project requirements, and then get from them what scenarios they are more interested in. Okay. So once you come up with the scenarios, they are prioritized using voting. So all these stakeholders, you provide them roughly 1/3 of the votes, and then they will vote for it. You come up with prioritized scenarios. You compare them from the utility tree that you have drawn in the previous 5th step. Okay. And what this tells us is, if there's a close match between the utility tree scenarios and the scenarios that the stakeholders have presented here, then that means there's good alignment, everybody's on the same page. But if there are additional scenarios, or if there's huge discrepancy, that means there is some disagreement, and we need to make sure that everybody's on the same page. We talk to each other and make sure it's all going through. Step 8, just like step 6, you will analyze the architectural approaches for each of the scenarios that you have prioritized from the previous step, and then you're going to come up with top 5 to 10 scenarios and go through it and understand the architectural decisions behind each one. Step 9, again the evaluation team will go away, they will talk to each other, They'll come back and then now they will present what they have discovered. Okay, so in terms of risks, in terms of risk themes, they will show all, they will then present it to the panel. They come up with all this. Okay, architectural approaches, they have documented scenarios and the prioritization, utility tree, risk, non-risk, sensitivity points, trade-off points, and they will distill all the risks that have been discovered into so-called risk themes that you can use so that you can refine your project or product. So again, this is very, very substantial undertaking. Lightweight is shortcut. As you can see, this can just take half a day or 1 day and you will. This is obviously less effort, less time, but obviously the output is also not as elaborate as the one that we get through ATAM. This slide and this diagram summarizes ATAM process very well. In ATAM process, you have business drivers, software architecture, is your start point. You come up with quality attributes and the scenarios. The software architecture, you're going to probe the approaches, the decisions, analyze them, and then you come up with trade-offs, sensitivity points, risks and non-risks. These risks are then combined into risk themes, and then this impacts the next iteration of this product. Okay, you're going to take it and feed it back into the system so that you can improve the architecture. Again, ATAM, probably control this. So this is modules. In module 8, we covered the process of design. So again, when we talk about design, we are going to solve problems, and we are going to make sure that when we solve problems, we are going to implement the system's requirements within the architectural structure, within the cost, and including the general principles of good quality. So process of design includes lots of design principles. And what this side is saying is this. When you look at decision-making process, you have a problem space, you have a decision space. Problem space is your main design problem. You break it into sub-problems, and each sub-problem you have alternative design options. You will choose the best option, which is the decision. Okay. So this is called decision space for the corresponding problem space. So again, you all should know this. When you make design decisions, the architect, whoever is making the design decisions, should be the domain specialist. They should know the requirements. They should know the design, technology, SC principles, and past experiences and knowledge, domain knowledge. Again, the goals of good design, obviously to increase profits, reducing cost, requirements have to be met. If it can accelerate development, that is great. The main thing is two ways they are also incorporated as part of these good design principles. So there are 11 design principles. We should know what each of them are. Let's start with the first one. Design principle 1, divide and conquer. You have a big problem. Okay. Divide and conquer is you take that big problem and you break it up into smaller sub-problems, because as you all know, dealing with a series of smaller things is more easy to deal with as well as to comprehend, right? You can take smaller pieces and you can have separate teams of people working on these smaller pieces. You can have different engineers who are specialized in that area working on those pieces, and you can also use the parts, reuse the parts if needed in the future. Increase cohesion where possible. Increased cohesion is the principle where we are going to keep together things that are related to each other, right? So we're talking in terms of functions, like methods, layers. You all know, layer pattern will keep together services in the same layer. And procedural is again like methods. Utility is like in Java you have the map utility class. So all this makes the systems, our subsystem, cohesive, keeps everything localized in the same area. Reduced coupling. This talks about interdependencies of interactions between different parts or different modules of the same system. Like we're going to reduce the interdependencies so that we can increase the localization of changes. Okay. We want to make sure that most of the changes will be local so that we can maintain the product easily. And some types of coupling, and see here, I'm not sure if we went through this, but if you look at common coupling, that means you're using global variables. We use global variables only when we have to. Okay. We have data, if you have common data, then you know you're going to store it in one place. External, the concept of a facade pattern, the concept of singleton patterns, they all are used for increasing coupling. For reducing coupling, not increasing. Design principle 4, keep the level of abstraction as high as possible. You all know this from object-oriented programming. Information hiding. You want to hide the details of your implementation and only expose the characteristics or attributes of the system that other systems need for interfacing. Okay, so we are going to use like get methods, set methods. We won't expose the inherent data directly to the other systems. That's called abstraction or information hiding. Increase reusability where possible. So this is more, we're going to use entire frameworks in other contexts. Okay, entire architecture frameworks we're going to reuse in other contexts. And the way we do this is make sure that we're going to generalize our design and not customize it in any way. Design principle 6, reuse existing design and code where possible. So this is reusing like patterns, reusing tactics, reusing code pieces so that we can use it in other programs. Okay? So not context but other programs, and we want to make sure that we do not clone. That means we don't take one method and clone it in 100 places, because if we do that, then maintainability is an issue. Okay, so that's something we don't consider as part of use. Design for flexibility. Again, all the principles we have seen so far, we're going to include this. We want to make sure we anticipate changes. We want to make sure that design can evolve in the future, and we include the design principles from before that we've already seen. We don't hard code, we leave options open. We use reusable code, make code reusable, and so on. So this is designing for flexibility. Anticipate obsolescence. In current day and age, it's very hard to anticipate this. We want to make sure that technology that we're going to use in our software system can run, or will continue to run, or can be changed easily. Okay, this is something that evolves very fast in today's day and age. So some of the key points here is avoid early releases of technology which may be buggy, which may be problematic. We want to avoid using any kind of undocumented features. We want to avoid software libraries that are environment specific. We want to avoid software or special hardware from companies. Again, if you don't have long-term support, that is a problem. And we want to make sure you use standard libraries and technologies that are supported by multiple vendors. We want to make sure there is standardization. Design for portability, we want to make sure that the software runs on different platforms. And if you have any kind of software just in one platform, you know that it will not run on other platforms. It's a problem. Design for testability, you want to make sure that you can take your system and you can test it using individual programs. Okay, so an example is, if you have a front-end user interface, which is graphical, you can remove the user interface and then tie up the rest of the system with just a main method, right? And then you can unit test the system using these methods so that you can catch bugs. Okay, and it will also make sure that this system is more robust. It will run in using any external program. Design defensively. Even though this is principle 11, I think there should be principle 1. In today's day and age, you have to make sure that you never trust others, and make sure that you're capturing the design in terms of understanding how that component is being used. We want to make sure that we are a little bit overzealous, like we have more enthusiasm doing this. We handle all the cases. that we think the component could be hacked into, and I think even though it's a little bit overzealous, that means we're very, very interested. It is actually good because you are incorporating defensive design in your product, which in today's day and age, as I said, you don't want to have any loopholes in the system. So 11 design principles, you can be asked questions on any of them, you should know how to answer. Then making good decisions, again we use priorities, we use objectives, right? So all the alternatives that we choose for design decision in the space of the decision space, you need to identify what the pros are, what the cons are, and this is something you are doing in your projects also, right? All these design decisions, which one you're going to choose. And then we adjust priorities so that we can use that particular design for the subsequent decision making and final implementations. There is one more pattern from chapter 13, which is MVC, Model View Controller Pattern. The context, obviously, in today's day and age, if you want different perspectives of your data on the front end side, and this is an interactive application, then you should be able to change these representations, right? As the changes happen to the underlying data, so it should be responsive, but you should maintain the functionality and the responsiveness separately, right? So how can we do this? The solution is MVC pattern. So we have model, the underlying data, view is the user interface or interaction with the user. Controller is also known as a director, it's known as a sequencer, and it mediates the control between the view and the model, and is what is used to direct the messages between the model and the view. This is the block diagram of MVC. As you can see, there's a view that interacts with the user. Controller is the sequencer. It communicates with the view, communicates with the model. Observe that the model does not communicate with the controller distinct. Controller is the one that communicates with the model. With the model, any kind of changes to the data is communicated back to the view, and the view can obviously query the state. Any kind of changes from the user is sent to the controller, and any kind of view selection from the controller goes to the model. So MVC, there's clear delineation in terms of its own layering, and controller is the director or the sequencer of the messages. You can see all what I've said here. So constraints, you can see this, and weaknesses, obviously MVC is a little bit more complex, and you invest in MVC if it's a complex user interface, and some older user interface toolkits may not gel well with the MVC abstraction, and in that case we need to provide some high-level wrappers so that you can use those systems. And in web architecture, use the browser, controller is the interpretation of HTML post, and model is the data in your backend. So hopefully you know this, there's MVC obviously is a reach design principle as well, so the TA probably went through this. In controllers and web application networks, there are model 1, model 2, and this was your homework question as well, so you need to know what the difference is. In model 1 architecture, in model 1, this JSP page has all the information for the view and for the model and local controller functionalities. Everything is incorporated in this one JSP page. This communicates with the browser, gets the information, and also sends the response. So in this kind of model 1 web architecture, the problem is this. It's suitable only for small applications because each JSP page stores each page implements its part in the part of the larger page flow, and each page decides which pages follow in the page flow. So the controller's implementation is spreading it throughout the design, which is very, very inefficient, right? So combining both presentation, application, and logic is it makes this model very inefficient. And in web architecture, use the browser, controller is the sequencer, it communicates with the view, and for the model, gets the information, and also sends the response. So in this kind of model 1 web architecture, the problem is So what we do is we enhance this model to web architectures. There's a controller servlet, typically a controller that gets the request from the user, and then this talks to the model and to the JSP page, and this JSP page is going to get the data and then communicate back to the browser. So this is more delineate control. Everything is not just focused on one component. So in Model 2 controller, again, you can have a state transition table, and since this does not hard code each application's controller implementation is each page, this is more data driven and this is more configurable. So this is widely used for vSWL web application framework. This is Model 2. And what is Struts? Struts uses Model 2 web application architecture, and you can see all the different concepts, but mainly this web browser. The input goes to this action servlet. This action servlet spawns actions. These actions then generate a form beam which gets the business logic. Through this business logic, the data store gets the data and then communicates it back to the JSP file. The JSP file then talks back to the browser and gives the information. So it's Model 2 web application architecture. So again, this is model, instructs. Model is the action classes. The view is the JSPs, and the controller is action servlet execution. And the structure configuration. So this is widely used in web application for reusability. Right? So what is?
Excuse me. How much do you make a year in New York?
What is that? Alright, so module 9 talks about security. So in this we spoke about several services, encryption, decryption. You should know what this is. What is symmetric encryption? One shared key. Public-private key encryption. This is asymmetric encryption. And then we looked at this. And again, when you use hashing, you can then reverse the order and you can make sure that the receiver is verifying the hash on their end, and therefore you can send secure documents. Secure online businesses, this uses a combo of private and public key. And you can see that in a diagram. So the browser sends a request to the server sends back the digital certificate, and then the browser and the server client and server communicate and connect to each other using the server's public key. Once the session is established, then they can securely send the information to each other. It's called SSL connection, secure socket link. Firewall, we went through this. Firewalls are tactics which provide gatekeeping, and this is between public internet and machines in the private networks. So we looked at this. A firewall will restrict all those addresses. You can do this custom. So you can allow certain addresses through and certain messages from certain sources, or you can restrict it. So two levels of firewall protection is typically there. A perimeter firewall and an internal firewall. So this is a perimeter firewall, this is internal firewall for the enterprise subnet. And to prevent hacks, what is oftentimes done is we can further partition this internal firewall for the DBMS subnet if this contains secure data, so that enterprise subnet users cannot access this data. Furthermore, you can also add service access restriction to only some people for the data. So this is called DBMS subnet, and you can provide system services. You can design them so that you can limit access to sensitive information. So what is a firewall? What it does, you should know. We looked at software security. We looked at this. What do you know what this is? Asset is economic value. Threat is to these assets. We need to get the stakeholder requirements, and then we need to make sure that when we create our security policy, it involves all this. So CIA, confidentiality, integrity, availability, this is widely used in security. When you look at threat modeling is rank risk by the impact of that particular risk and the likelihood of its happening, then you prioritize the threat and then accordingly we mitigate the effect. Something you've gone through. So security again with different techniques. In security you can be asked questions on there and what is security in terms of policies. Module 10, we looked at the concept of architecture reconstruction. So this is what we said in terms of reverse engineering to recover lost information and also to provide proper system documentation in case that information is missing, assisting with maintenance because if there are problems, we want to make sure that we're capturing that and we are refactoring the code and so on. Migration to another platform. If it's a new platform, we'll have to do abstraction and then move it to the new platform. Facilitating software reuse. Make sure that any kind of documentation that you come up with, facilitating that kind of reuse for the future. So this is chapter 20, again reconstruction, we went through all this. Documentation is not there. Your system evolved and the documentation has not evolved. We want to make sure it's capturing all that. Various techniques. We're going to involve human experts. We're going to involve pattern, static dynamic analysis. We're going to compare products within families. So it's a combination of tools and human experts. Again, shows the tool intensive activity, so we need tools. So this is what you need to know what the 4 phases are. Okay. The first one is raw view extraction. I'm going to go through this. So in raw view extraction, we are taking the artifacts that we have and then we're going to analyze them and we're going to create we're going to come up with a set of facts. These set of facts will give us some kind of relationships between the various artifacts. Maybe you can come up with layering and so on. You come up with static information, you come up with dynamic information, and you get some idea about what these set of facts are. Database construction. Now these set of facts is not very comprehensible, that's what's called white noise. Some of them are not even standardized, so they have different standards and things like that, it's very confusing. So what we do is take all these information that we've captured and we are going to store them in a database. We use a database, store the extracted information, and so we can use this data, especially if it's large, and then we can employ tools to act on this data. View fusion is we're going to fuse views. So you take static views, you combine them with dynamic views. So this gives you a more holistic information about the system. And creating fused views, then you can come up with some kind of a hypothesis. Okay, so you can come up with some kind of idea of what the architecture is. Finding violations. Step 4 is testing. So you have come up with a hypothesis, you're testing to make sure this is conforming with the architect's intentions, you're coming with the correct architecture decision, and you can use tools to find such violations. So you went through this, if there's any violation like this, it will capture. So you can use tools to find these violations, both static violations or dynamic violations. Dynamic violations in terms of this piece here for a database, right? It should only be MTBs, but here it is. Session. Okay. So things like this you can capture in the 4th step. So again, if the 4th step is showing significant errors, then that means you have to go back and redo the process. Okay, so that is what this is telling you. The 4 steps, again you should know what these are. Raw view extraction, construction of database, view fusion, architecture analysis. So, chapter 11, we looked at the concept of quality attribute analysis. And why we need to do this is, several times we fail to the quality goes because of all these problems, right? And we went through all this. We also went through module 12 last time. This is chapter 14. So in chapter 2, we said that the importance of software architecture is analysis of the architecture enables early prediction of systems quality. So if we can get some kind of analysis early on, then we can predict the systems qualities early on. And then there are different methods. I mean, you should know all these methods. Some of these methods are analytical models, and it supports quantitative analysis, like for example, studying performance, studying availability. These are well-studied models. We went to performance models. So for this QA called performance, there's a QE model. Using QE model and an MVC pattern allocation, we can come up with some kind of statistics for measuring the latency characteristics of this system, right? And once you come up with the statistics using this QE model, I'll do this, right? We can easily predict latency of the system. But this is only worthwhile if your cost is, if you have benefit and wherever the latency is important and you want to really spend time on it. Second QA, that is well studied availability. We looked at this in the concept of a broker pattern using redundancy tactics. We looked at a active redundancy, which is a hot spare, where the broker spare and the broker active are synchronized between each other, so they are exactly mirrored copy of each other. Passive redundancy is the concept of a warm spare, where the broker spare is synced up with the active broker through periodic checkpointing. Okay, it's not an exact mirror, but it has some kind of a failover mechanism in case your broker active fails. And the cold spare is the case where your broker spare is just sitting cold, and you have to cover this up in order to, if your broker active fails. So the active redundancy, passive cold. And then you use probabilities, you use math, and then you can come up with some kind of statistics, and then you can see in what case you're using what tactic works for you in your system. Quality attribute checklist is the third way you can perform quality attribute analysis. You can check requirements, you can audit, and these checklists are sometimes very vast. Okay, they can defeat the purpose of even using them, as we looked last time. But this will provide you guidelines for the architect to make sure that you have requirements that are understood and prioritized. If there's audit happening, we use this for certification. So checklists are very useful in the industry. And this thought experiment, this is like we are thinking through the scenario verbally, and we're writing this down. The thought experiment is something like this. You could write the steps on a board along with your friend. You can discuss this mentally in your own mind. You can write it down. The main goal is you're going to check if any problems are there, issues, like what can go wrong. You're considering several different QAs simultaneously. Then the main reason is rough analysis. We are not going to do deep analysis of this unit. Looked at experiments, simulations, prototype. These are exploration of trade-offs. These are different ways you can analyze the system. You can design experiments in the development phase and make sure that your project is going to include these experiments as test cases, and you can measure them. Simulations, you can simulate the loads using flying simulators, instrumentation loads, etc. So that you can provide some kind of load to the system and stress test it, load test it, etc. Then you can also use fault injection tools. We told you prototype alternatives. You can implement skeletal systems, and you can test out the system early on. You can use different analysis at different parts of the cycle. We already went through this. Analysis, thought experiments with simulations, prototypes, models, measurement. We also went to check this. Okay. quality attribute analysis. Yeah, almost out of time. Finance fishbone diagram. You know, you cannot draw a fishbone, but if a fishbone is given to you or any questions come like that. So fishbone, you all know it resembles the shape of a fish. We already looked at this. So these are examples, Purvias mileage. So when you read diagrams, you know the main spine. These are the primary causes. These are the main categories. You can add details. Right, we went through this. These are secondary causes. These are tertiary causes. You can add more details to the fishbone diagram. And furthermore, you can also analyze the diagram. You can eliminate non-causes. That's your first step, right? So anything that the team thinks or you think that is not a cause, remove it. How likely is the cause really there and will influence the system? How easy it is to verify. You have 3 analysis phases. As an example of non-cause, you are eliminating causes that you think that not relevant. Then adding weighting for the how likely, that is the second weighting. Somewhat likely, very likely, not likely. And then the last one is how easy it is to verify. We'll add the second thing. And then what your goal is to start with this. Very likely and very easy to verify. We start with these and then we go to that and then we will implement solutions and try to solve the problems of the system. Okay. So this is called fishbone diagram.